So we will move on with the questions. So some of you asked the question through the chat box, so you had already some answers, but I suggest we go over the questions again. So first, Ricardo, so you mentioned the heat penalty was about equal to the cooling savings in the coolest locations in Australia. Does it mean it would be the case for most European countries with high heating loads, even with insulated roofs?
Thank you for the question. No, it will be different. That was a case of an uninsulated office building, so it's in the most unfavorable situation. If you have a high insulation, of course, that will be different because you're minimizing the heat transfer through the building envelope. Also, if you look into the paper, we consider the currently required insulation levels in Australia, which are way lower than the R values. So the thermal resistances required here are way lower than those required in cold countries in Europe. So if you get to use 20 centimeters insulation, the difference would be minimal. So it wouldn't have an impact. So that was in the most unfavorable situation for the existing building stock for uninsulated office buildings.
Okay.
Also, the other thing to bear in mind is that once we go towards even for houses, we were showing for new houses which in Australia do not have very high insulation levels. If we move to higher insulation levels, we are minimizing the impact, but also even if we are not increasing very much the insulation levels, but we can do other things like putting some heat recovery ventilation. So we are differentiating the strategy. We're not having the same sort of response with the same kind of strategy all throughout the year. So we can diversify the mechanisms to achieve energy conservation.
Okay,
Thanks.
thank you. And the next question is, will this material have an effect on the energy generated by photovoltaic system at the rooftop of the building? Understanding that this material absorbs thermal energy upon emission, which would enhance the cooling potential to the building. So you already gave an answer, but can you go over it again, please?
Yeah, so depending on, of course, if it's just one standalone building with a small roof, we would have only the contribution of the short-wave radiation reflected towards the PV panel, but that it, of course depends also on the wavelength, on the type of roof which is used, and also on the type of installation, whether it's a rack-mounted roof or not. So if we have a backscattering towards the PV panels or not. In terms of reduction of the temperature loss of the PV, of course, it depends whether it's a small, just one building with a roof, then the effect is minimal, is negligible. If we have a very large building, we saw the effect on HVAC. If we have all buildings in the area, we are reducing the urban air temperature, and therefore we are reducing the temperature losses of PV. Likewise, if when you compare the energy yield, the electricity yield of PV in different environmental conditions. Mats, do you want to add something on it?
This is a very interesting question. First, we have to know that, for example, according to measurements and also simulations, the surface temperature of photovoltaics during summer in Sydney can be as high as 80 degrees, 80. Under these conditions, photovoltaics, they lose almost 20 to 25% of their performance. The use of cool roofs, and there are many experiments, especially in Arizona, in the United States. The use of cool roof, even in individual buildings, may improve the performance, of the photovoltaics up to, let's say, 4 or 5%, which is very important. But the most important thing is that, photovoltaics, because of the very high surface temperature, increase tremendously the release sensible heat to the atmosphere. So may increase the temperature up to 1.5 degrees. So the use of photovoltaics, especially in warm cities, may increase the temperature, of the city 1 to 1.5 degrees, and this really amortize in a way the benefits. So the use of cool materials, has a tremendous potential because it cools down, the temperature around the photovoltaic, so improve the performance, increases also the reflected radiation, as Ricardo said. But the most important is that decreases the sensible heat to the atmosphere. And this is the major problem, and in the future, and especially in the European South, because of this, I'm sorry to say, catastrophic, let's say, policy that is applied now in the European Union to install photovoltaics everywhere in the southern European cities, temperatures will increase up to 2.5 degrees, and this will be a tremendous impact on, let's say, the cooling performance of the city.
Okay, thank you very much for this answer. So now for Jifeng, you have 3 questions. The first one is, in your simulation, are you already including supercool materials or the first generation of cool materials? Are you there, Ji? Yes. Do you want to add something? Yes.
Can you hear me?
Yes, we can hear you.
Yeah, the cool materials we simulated in the weather research forecasting model, as you can see in I have presented the table giving the parameters for the 3 different supercool materials. And because we can't specify the parameters for different wavelengths, so we just used the parameter for the broadband radiative cooler. The broadband radiative cooler, which I presented in my presentation, it was one of the ideal radiative cooler as well. And whether the selective is better or the broadband is better, it depends on the specific climate. Yes, we've simulated the broadband ones and to facilitate the simulation in weather research forecasting model.
Okay. And
if you allow me, Valerie, if you allow me to say something here, which is very important. The actual, energy simulation, let's say, tools for buildings do not allow to change, the spectral, let's say, values of the emissivity. Yeah. So, and it is very difficult to have, a spectral selective, to simulate a spectral selective, material. Perhaps in the future this will be done, but for the time being, simulations can be performed only, for a standard, let's say, emissivity value.
Okay, thank you. And do these materials emit over time when exposed to the environment and erosion from natural elements? PFCs are bad news for the environment.
What is PFC standing for? May I ask the person who asked the question?
It's a component, so let's see. I cannot. Perfluorine. I don't know how to pronounce this. Do you have it here?
Yes, of course. If the material has certain emissivity in certain wavelengths, it will keep emitting all the time. It doesn't matter whether it is exposed to the sun or not. That is the first question. Erosion from natural elements. Sure, that is one of the major concerns about the weather fastness of the material, whether it's going to be influenced by the weather or other kind of elements in the long term. So we have some new functions of the radiative cooling material, such as self-cleaning or such kind of similar functions to prevent the erosion from natural elements. But that is subject to time to prove what kind of material have has better performance. Yeah, that is still a concern, and people are still exploring the different possibilities.
I add something here.
Yes,
These
sure.
materials do not have any chemical emissions. Perhaps the one that asked this question has, let's say, confused between chemical emissions and infrared radiation. It's completely different. You know, we don't have any chemical emissions here, and for sure we don't have PFCs. No one mentioned this. Okay, there's no way to have PFCs here. These are materials, you know, like common paints or whatever, but we don't have any chemical emissions here.
Okay, thank you. So you were asked to share the link source for the company that sells these materials. So you gave the link. I don't think, do you want to add something about this, or do we move to
the link?
Okay, perfect. Do you have any idea what the lifetime of radiative cooling materials is or could be? Secondly, I also wanted to ask if these materials can replace an existing layer of a roof built up, or are they always an additional layer?
First, about the lifetime of radiative cooling materials, because it hasn't been commercialized in a very wide range, so we don't have the chance to get to test what is the lifetime of the radiative cooling materials. According to the website and according to my colleagues who have communicated with the salesman of the company, they said around 20 to 50 years, depending on the material type. Painting, sprays, and films, they have different lifespans. And secondly, about whether this material can replace an existing layer, or they can, or they're always the additional layer. I think, if you remember, I've talked about the different functions being added to the material, like the fire resistance, the insulating property, and for the time being, I think it's just a cooling layer. The mechanical performance, the fire resistant performance, they are we need time to check what kind of performance they have. But later, as we have more functions added to the materials, it is possible that they can replace the existing layers and covering all the necessary properties of the existing roof layer. Yeah, that's my thought about this question.
Allow me to say something. Different types of radiative materials. You can have paints, for example. Imagine that you have, you know, some metal roofs which are painted with, you know, a radiative cooler. In this case, you don't have any, let's say, additional layer. You may have, you know, a solid surface. In this case, you need to have, let's say, an additional layer. Depends on the type of material you may have. Everything is possible. But you may have, you know, very simple materials like paints, which are now commercially available. You may have plastics, for example, like the one that GA Radicool has really distributed. And to avoid, you know, the problem of advertisement, I have to tell you that more than 5-6 companies all around the world that they produce similar results and similar products. You may have liquids, you may have different, let's say, materials. So depends on the type of roof you may wish to have.
Okay, thank you. So we have only 3 minutes left and a few more questions. Samira, any attempt to study the potential competition between supercool roofs and rooftop photovoltaics? Namely, where would it be best for a city household to go for one technology in lieu of the other? Do you have a rather quick answer to this question?
We should see this question from two aspects. First is the impact on the urban microclimate, and second is on the energy. For sure, PVs are generating energy, but in terms of the impact on the local urban climate, it is now proven that PVs will have an adverse impact on the urban climate. They will increase the ambient temperature, while cool materials especially in very hot climates, and can have a positive impact, can really decrease the ambient temperature, and which can have a corresponding impact also on energy. But in terms of like the energy, definitely we have the energy generation of cool roofs, and nowadays we are using cool roofs and PVs together, because the application of PVs and the energy generation by PVs can be enhanced when they are used in combination with cool roofs, because with the application of cool roofs we can reduce the ambient temperature, and this will this has a direct relation with the efficiency of solar cells. So when the ambient temperature decreases, the efficiency of solar of PVs increase. Also with cool roofs we are reflecting the light. That means that the solar PVs will receive higher incoming radiation through cool roofs. So I would say like nowadays they are really trying to use combine a strategy of using both PVs and cool roofs, but we should be very careful that eventually these PVs will have an adverse impact also on the urban climate.
Correct. If you allow me two additional, words. First, actually, there is a tremendous research to implement, super cool materials on the photovoltaics. In this case, we can cool down, the photovoltaics. So the next generation of photovoltaics will include also super cool materials, including photonic and also fluorescent materials, to cool down, the photovoltaics. There is no dilemma, photovoltaics or cool roof materials. It depends on the conditions, Depends also on, let's say, the characteristics of the cities. In, let's say, hot, warm climates, the use of photovoltaics has a tremendous impact on the environment. In, let's say, cool climates, in heating-dominated climate, there is not such a problem. So it depends on the conditions. But as Amira said, we have to consider, especially in warm cities, the tremendous impact of photovoltaics at large scale, on the overheating, and also the increase of the cooling demand of the building because of the installation of photovoltaics. Although many people, they believe that because of the shading of the photovoltaics, to the roof, the cooling demand of the buildings is decreasing. In reality, it is increasing. It is increasing because the building cannot emit radiation, especially from the roof during the night, because it is, let's say, reflected back from the photovoltaics. And all the measurements we have in warm climates shows that the cooling demand of the building is really increasing when we have photovoltaics. So we have to be very careful on this, and depends, on the conditions.
Okay, thank you very much, Matt. We have a few questions for all panelists. What about the cost of supercool materials and the return on investment time depending on the climate? You want to say a word on this? Who would like to? Yes, please, Matt.
Actually, the cost of the materials which are commercialized is very low. It's very similar, to the cost of the conventional materials, because there is no something very expensive, in the fabrication of these materials. We use these materials because, let's say, we like to test different materials that are available to the market. The cost is really very low. It's very similar to the cost of a normal paint. The cost is so low that we cannot discuss about, amortization of the investment. It's almost nothing. In reality, it is, let's say, the less expensive energy conservation technology that exists actually, in the world.
Okay, thank you. Someone asked if to advance this research, are you open for collaboration, especially on the impact of these cooling materials on PV?
Always.
So someone asked if it was possible to share the presentation. So yes, they will be available by the end of the week on the AIVC website. One comment that PVT technology will also help to cool the PV panels. And we will just go back. I believe we have one more question for Ricardo. So I was wondering if a cool roof on a very high building with no other cool roofs in the city can also lower the ambient air temperature of the surrounding of the building, or does the ambient temperature around the buildings only drop when more cool roofs are used in a region?
Thank you for the question, Nick. Of course, you will need more cool roofs in the region. Of course, you have like the extremes. So if you have like just the top of the Burj Khalifa to present an extreme case with a cool roof, the impact on the air temperature at 2 meters at pedestrian level is negligible. If you have a very let's say shopping mall with a single building, which is with a very large footprint, and it's a roof, and it's not that tall. It still mitigate around, but just around the rooftop. And the rest is all in between the extremes, and of course it is most effective if you see many buildings around. And now we don't share it the presentation anymore, but then when you will see in the slides and also in the paper, you see that in Sydney you have a remarkable air temperature reduction when you have a clusters of buildings all with a cool roof. At the fringes of the urban areas where you have like just some urban sprawl or just some isolated buildings here and there, you see a reduction in land surface temperature, but you do not see a reduction or a non-negligible reduction in air temperature, just because there are just a few buildings here and there that are too isolated to produce a drop in temperature.
Okay.
Thank you for the question.
Thank you very much.